Chapter 12. Fundamentals of Electricity and Electronics. Introduction. This chapter addresses the fundamental concepts that are the building blocks for advanced electrical knowledge and practical troubleshooting. Some of the questions addressed are: how does energy travel through a copper wire and through space? What is electric current, electromotive force, and what makes a landing light turn on or a hydraulic pump motor run? Each of these questions requires an understanding of many basic principles. By adding one basic idea on top of other basic ideas, it becomes possible to answer most of the interesting and practical questions about electricity or electronics. Our understanding of electrical current must begin with the nature of matter. All matter is composed of molecules. All molecules are made up of atoms, which are themselves made up of electrons, protons, and neutrons. 12-1. General composition of matter. Matter can be defined as anything that has mass and volume, and is the substance of which physical objects are composed. Essentially, it is anything that can be touched. Matter is what all things are made of, whatever occupies space, has mass, and is perceptible to the senses in some way. Weight is an indirect method of determining mass, but it is not the same. Weight is a measure of the pull of gravity acting on the mass of an object. The more mass an object has, the more it weighs under the Earth's force of gravity. Mathematically, weight can be stated as follows: weight equals mass times gravity. Categories of matter are ordered by molecular activity. The four categories or states are solids, liquids, gases, and plasma. For the purposes of the aircraft technician, only solids, liquids, and gases are considered. Element. An element is a substance that cannot be reduced to a simpler form by chemical means. Iron, gold, silver, copper, and oxygen are examples of elements. Beyond this point of reduction, the element ceases to be what it is. Compound. A compound is a chemical combination of two or more elements. Water is one of the most common compounds, and is made up of 2 hydrogen atoms and 1 oxygen atom. Molecule. The smallest particle of matter that can exist and still retain its identity, such as water, H2O, is called a molecule. Figure 12-1. Substances composed of only one type of atom are called elements. But most substances occur in nature as compounds, that is, combinations of 2 or more types of oxygen atom, nucleus electrons, hydrogen atoms. Figure 12-1. A water molecule. Atoms. It would no longer retain the characteristics of water if it were compounded of 1 atom of hydrogen and 2 atoms of oxygen. If a drop of water is divided and then divided again and again until it cannot be divided any longer, it is still water. Atom. The atom is considered to be the most basic building block of all matter. Atoms are composed of 3 subatomic particles: protons, neutrons, and electrons. These 3 particles determine the properties of the specific atoms. Elements are substances composed of the same atoms with specific properties. Oxygen is an example of this. The main property that defines each element is the number of neutrons, protons, and electrons. Hydrogen and helium are examples of elements. Both of these elements have neutrons, protons, and electrons but differ in the number of those items. This difference alone accounts for the variations in chemical and physical properties of these 2 different elements. There are over 100 known elements in the periodic table. Figure 12-2. They are categorized according to their properties on that table. The kinetic theory of matter also states that the particles that make up the matter are always moving. Thermal expansion is considered in the kinetic theory, and explains why matter contracts when it is cool, and expands when it is hot, with the exception of water/ice. Electrons, protons, and neutrons. At the center of the atom is the nucleus, which contains protons and neutrons. Protons are positively charged particles, and neutrons are neutrally charged particles. A neutron has approximately the same mass as the proton. The third particle of the atom is the electron, that is a negatively charged particle with a very small mass compared to the proton. The proton's mass is approximately 1,837 times greater than the electron. Due to the proton and the neutron location in the central portion of the atom, nucleus, and the electron's position at the distant periphery of the atom, it is the electron that undergoes the change during chemical reactions. Since a proton weighs approximately 1,845 times as much as an electron, the number of protons and neutrons in its nucleus determines the overall weight of an atom. The weight of an electron is not considered in determining the weight of an atom. Indeed, the nature of electricity cannot be defined clearly because it is not certain whether the electron is a negative charge with no mass, weight, or a particle of matter with a negative charge. Hydrogen represents the simplest form of an atom. Figure 12-3. At the nucleus of the hydrogen atom is 1 proton, and at the outer shell is 1 orbiting electron. At a more complex level is the oxygen atoms. which has 8 electrons in 2 shells orbiting the nucleus with 8 protons and 8 neutrons. Figure 12-4. When the total positive. 12-2. Figure 12-2. Periodic table of elements. Electron. 8 protons 8 neutrons. Nucleus. 1 proton. Figure 12-3. Hydrogen atom. Charge of the protons in the nucleus equals the total negative charge of the electrons in orbit around the nucleus. The atom is said to have a neutral charge. Electron shells and energy levels. Electrons require a certain amount of energy to stay in an orbit. This particular quantity is called the electron's energy level. By its motion alone, the electron possesses kinetic energy, while the electron's position in orbit determines its potential energy. The total energy of an electron is the main factor that determines the radius of the electron's orbit. Figure 12-4. Oxygen atom. Electrons of an atom appear only at certain definite energy levels, shells. The spacing between energy levels is such that when the chemical properties of the various elements are catalogued, it is convenient to group several closely spaced permissible energy levels together into electron shells. The 12-3. Maximum number of electrons that can be contained in any shell or sub-minus shell is the same for all atoms, and is defined as electron capacity equals 2n2. In this equation, n represents the energy level in question. The first shell can only contain 2 electrons. The second shell can only contain 8 electrons. The third, 18. And so on until we reach the 7th shell for the heaviest atoms, which have 6 energy levels. Because the innermost shell is the lowest energy level, the shell begins to fill up from the shell closest to the nucleus and fill outward as the atomic number of the element increases. However, an energy level does not need to be completely filled before electrons begin to fill the next level. The periodic table of elements should be checked to determine an element's electron configuration. Valence electrons. Valence is the number of chemical bonds an atom can form. Valence electrons are electrons that can participate in chemical bonds with other atoms. The number of electrons in the outermost shell of the atom is the determining factor in its valence. Therefore, the electrons contained in this shell are called valence electrons. Ions. Ionization is the process by which an atom loses or gains electrons. Dislodging an electron from an atom causes the atom to become positively charged. This net positively charged atom is called a positive ion or a cation. An atom that has gained an extra number of electrons is negatively charged and is called a negative ion or an anion. When atoms are neutral, the positively charged proton and the negatively charged electron are equal. Free electrons. Valence electrons are found drifting midway between 2 nuclei. Some electrons are more tightly bound to the nucleus of their atom than others, and are positioned in a shell or sphere closer to the nucleus, while others are more loosely bound and orbit at a greater distance from the nucleus. These outermost electrons are called free electrons because they can be easily dislodged from the positive attraction of the protons in the nucleus. Once freed from the atom, the electron can then travel from atom to atom, becoming the flow of electrons commonly called current in a practical electrical circuit. Electron movement. Conductors, insulators, and semiconductors. The valence of an atom determines its ability to gain or lose an electron, which ultimately determines the chemical and electrical properties of the atom. These properties can be categorized as being a conductor, semiconductor, or insulator, depending on the ability of the material to produce free electrons. When the material has a large number of free electrons available, a greater current can be conducted in the material. Conductors. Elements such as gold, copper, and silver possess many free electrons and make good conductors. The atoms in these materials have a few loosely bound electrons in their outer orbits. Energy in the form of heat can cause these electrons in the outer orbit to break loose and drift throughout the material. Copper and silver have 1 electron in their outer orbits. At room temperature, a piece of silver wire has billions of free electrons. Insulators. Insulators are materials that do not conduct electrical current very well or not at all, such as glass, ceramic, and plastic. Under normal conditions, atoms in these materials do not produce free electrons. The absence of free electrons means that electrical current cannot be conducted through the material. Only when the material is in an extremely strong electrical field will the outer electrons be dislodged. This action is called breakdown, and usually causes physical damage to the insulator. Semiconductors. The material properties of semiconductors fall in between conductors and insulators. In their pure state, they are not good at conducting or insulating. Semiconductors can operate like a conductor or insulator depending on what external load is placed on the material. Semiconductors are used to make transistors and integrated circuits. Silicon and germanium are the most widely used semiconductor materials. For a more detailed explanation on this topic, refer to page 12-98 in this chapter. Metric-based prefixes used for electrical calculations. In any system of measurements, a single set of units is usually not sufficient for all the computations involved in electrical repair and maintenance. Small distances, for example, can usually be measured in inches, but larger distances are more meaningfully expressed in feet, yards, or miles. Since electrical values often vary from numbers that are a millionth part of a basic unit of measurement to very large values, it is often necessary to use a wide range of numbers to represent the values of units, such as volts, amperes, or ohms. A series of prefixes that appear with the name of the unit have been devised for the various multiples or submultiples of the basic units. There are 12 of these prefixes, which are also known as conversion factors. 4 of the most commonly used prefixes in electrical work are 12-4. Mega, M, means 1 million, 1 million. Kilo, K, means 1,000, 1,000. Milli, M, means 1,000th, 1/1000. Micro, mu, means 1 millionth, 1/1 million. Kilo is one of the most extensively used conversion factors. It explains the use of prefixes with basic units of measurement. Kilo means 1,000, and when used with volts, is expressed as kilovolt, meaning 1,000 volts. The symbol for kilo is the letter K. Thus, 1,000 volts is 1 kilovolt or 1 kV. Conversely, 1 volt would equal 1,000th of a kV, or 1/1000 kV. This could also be written 0.001 kV. Similarly, the word milli means 1,000th, and thus, 1 millivolt equals 1,000th, 1/1000, of a volt. Figure 12-5 contains a complete list of the multiples used to express electrical quantities, together with the prefixes and symbols used to represent each number. Static electricity. Electricity is often described as being either static or dynamic. The difference between the two is based simply on whether the electrons are at rest, static, or in motion, dynamic. Static electricity is a buildup of an electrical charge on the surface of an object. It is considered static due to the fact that there is no current flowing as in alternate current, AC, or direct current, DC, electricity. Static electricity is usually caused when non-conductive materials, such as rubber, plastic, or glass, are rubbed together, causing a transfer of electrons, which results in an imbalance of charges between the two materials. The fact that there is an imbalance of charges between the two materials means that the objects will exhibit an attractive or repulsive force. Number prefix symbol 1,000,000 tera T 1 billion giga G 1 million mega M 1000 kilo K 100 hecto H 10 deka DK 0.1 desa D 0.01 centi C 0.001 milli M 0.0000001 microsign 0.000000001 nano and 0.00000000001 pico P. Attractive and repulsive forces. One of the most fundamental laws of static electricity, as well as magnetics, deals with attraction and repulsion. Like charges repel each other and unlike charges attract each other. All electrons possess a negative charge, and as such repel each other. Similarly, all protons possess a positive charge, and as such repel each other. Electrons, negative, and protons, positive, are opposite in their charge and attract each other. For example, if two pith balls are suspended, as shown in figure 12-6, and each ball is touched with the charged glass rod, some of the charge from the rod is transferred to the balls. The balls now have similar charges and, consequently, repel each other as shown in part B of figure 12-6. If a plastic rod is rubbed with fur, it becomes negatively charged and the fur is positively charged. By touching each ball with these differently charged sources, the balls obtain opposite charges and attract each other as shown in part C of figure 12-6. Although most objects become charged with static electricity by means of friction, a charged substance can also influence objects near it by contact. Figure 12-7. If a positively charged rod touches an uncharged metal bar, it draws electrons from the uncharged bar to the point of contact. Some electrons enter the rod, leaving the metal bar with a deficiency of electrons, positively charged, and making the rod less positive than it was, or, perhaps, even neutralizing its charge completely. A method of charging a metal bar by induction is demonstrated in figure 12-8. A positively charged rod is brought near, but does not touch, an uncharged metal bar. Electrons in the metal bar are attracted to the end of the bar nearest the positively charged rod, leaving a deficiency of electrons at the opposite end of the bar. If this positively charged end is touched by a neutral object, electrons will flow into the metal bar and neutralize the charge. The metal bar is left with an overall excess of electrons. Electrostatic field. A field of force exists around a charged body. This field is an electrostatic field, sometimes called an electric field. and is represented by lines extending in all directions from the charged body, and terminating where there is an equal and opposite charge. To explain the action of an electrostatic field, lines are used to represent the direction and intensity of the electric field of force. As illustrated in figure 12-9, the intensity of the field is indicated by the number of lines per unit area, and the direction is shown by arrowheads on the lines pointing in the direction in which a small test charge would move, or figure 12-5. Prefixes and symbols for multiples of basic quantities tend to move if acted upon by the field of force. 12-5. Charge rod. Pith balls. A. Electrons are attracted by positive charge. Positively charged rod almost touching uncharged bar. When rod touches bar, electrons enter rod. Metal bar now has positive charge. The rod is now less positively charged. B. Repulsion. Figure 12-7. Charging by contact. C. Attraction. Figure 12-6. Reaction of like and unlike charges. Either a positive or negative test charge can be used, but it has been arbitrarily agreed that a small positive charge is always used in determining the direction of the field. Thus, the direction of the field around a positive charge is always away from the charge, because a positive test charge would be repelled. Figure 12-9, on the other hand, the direction of the lines about a negative charge is toward the charge, since a positive test charge is attracted toward it. Figure 12-10 illustrates the field around bodies having like charges. Positive charges are shown, but regardless of the type of charge, the lines of force would repel each other if the charges were alike. The lines terminate on material objects, and always extend from a positive charge to a negative charge. These are imaginary lines used to show the direction a real force takes. Electrons are attracted toward charged rod. Electrons are attracted off finger and enter bar. Finger is removed. Positive and negative charges are mostly neutralized. Rod is removed and excess electrons remain. Figure 12-8. Charging a bar by induction. 12-6. Inside surface neutral. Figure 12-9. Direction of electric field around positive and negative charges. Figure 12-10. Field around two positively charged bodies. It is important to know how a charge is distributed on an object. Figure 12-11 shows a small metal disc on which a concentrated negative charge has been placed. By using an electrostatic detector, it can be shown that the charge is spread evenly over the entire surface of the disc. Since the metal disc provides uniform resistance everywhere on its surface, the mutual repulsion of electrons results in an even distribution over the entire surface. Another example, shown in figure 12-12, is the charge on a hollow sphere. Although the sphere is made of conducting material, the charge is evenly distributed over the outside surface. The inner surface is completely neutral. This, figure 12-12, charge on a hollow sphere phenomenon is used to safeguard operating personnel of the large Van de Graaff static generators used for atom smashing. The safest area for the operators is inside the large sphere, where millions of volts are being generated. The distribution of the charge on an irregularly shaped object differs from that on a regularly shaped object. Figure 12-13 shows that the charge on such objects is not evenly distributed. The greatest charge is at the points, or areas of sharpest curvature, of the objects. Electrostatic discharge (ESD) considerations. One of the most frequent causes of damage to a solid-state component or integrated circuits is the electrostatic discharge (ESD) from the human body when one of these devices is handled. Careless handling of line-replaceable units, LRUs, circuit cards, and discrete components can cause unnecessarily time-consuming and expensive repairs. This damage can occur if a technician touches the mating pins for a card or box. Other sources for ESD can be the top of a toolbox that is covered with a carpet. Damage can be avoided by discharging the static electricity from your body by touching the chassis of the removed box, by wearing a grounding wrist strap, and exercising good professional. Greatest charge. Figure 12-11. Even distribution of charge on metal disc. Figure 12-13. Charge on irregularly shaped objects. 12-7. Handling of the components in the aircraft. This can include placing protective caps over opened connectors, and not placing an ESD-sensitive component in an environment that causes damage. Parts that are ESD-sensitive are typically shipped in bags specially designed to protect components from electrostatic damage. Other precautions that should be taken with working with electronic components are: 1. Always connect a ground between test equipment and circuit before attempting to inject or monitor a signal. 2. Ensure test voltages do not exceed maximum allowable voltage for the circuit components and transistors. 3. Ohmmeter ranges that require a current of more than 1 milliampere in the test circuit should not be used for testing transistors. 4. The heat applied to a diode or transistor, when soldering is required, should be kept to a minimum by using low-wattage soldering irons and heat sinks. 5. Do not pry components of a circuit board. 6. Power must be removed from a circuit before replacing a component. 7. When using test probes on equipment and the space between the test points is very close, keep the exposed portion of the leads as small as possible to prevent shorting. Magnetism. Magnetism is defined as the property of an object to attract certain metallic substances. In general, these substances are ferrous materials. That is, materials composed of iron or iron alloys, such as soft iron, steel, and alnico. These materials, sometimes called magnetic materials, include at least 3 non-ferrous materials: nickel, cobalt, and gadolinium, which are magnetic to a limited degree. All other substances are considered non-magnetic. A few of these non-magnetic substances can be classified as diamagnetic, since they are repelled by both poles of a magnet. Magnetism is an invisible force, the ultimate nature of which has not been fully determined. It can best be described by the effects it produces. Examination of a simple bar magnet similar to that illustrated in Figure 12-14 discloses some basic characteristics of all magnets. If the magnet is suspended to swing freely, it aligns itself with the Earth's magnetic poles. One end is labeled N, meaning the north-seeking end or pole of the magnet. If the end of a compass or magnet is referred to as north-seeking rather than north, there is no conflict in referring to the pole it seeks, which is the north magnetic pole. The opposite end of the magnet, marked S, north pole, south pole. Figure 12-14. One end of magnetized strip points to the magnetic north pole, is the south-seeking end, and points to the south magnetic pole. Since the Earth is a giant magnet, its poles attract the ends of the magnet. These poles are not located at the geographic poles. The somewhat mysterious and completely invisible force of a magnet depends on a magnetic field that surrounds the magnet. Figure 12-15. This field always exists between the poles of a magnet and arranges itself to conform to the shape of any magnet. The theory that explains the action of a magnet holds that each molecule making up the iron bar is itself a tiny magnet, with both north and south poles as illustrated in Figure 12-16a. These molecular magnets each possess a magnetic field. Lines of force. NNS. S. Figure 12-15. Magnetic field around magnets. 12-8. NS. SN. SN. NS. NS. SN. NS. 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 SN. NS. 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 B. Unmagnetized magnetized. Figure 12-16. Arrangement of molecules in a piece of magnetic material. But in an unmagnetized state, the molecules are arranged at random throughout the iron bar. If a magnetizing force, such as stroking with a lodestone, is applied to the unmagnetized bar, the molecular magnets rearrange themselves in line with the magnetic field of the lodestone, with all north ends of the magnets pointing in one direction, and all south ends in the opposite direction. Figure 12-16b. In such a configuration, the magnetic fields of the magnets combine to produce the total field of the magnetized bar. When handling a magnet, avoid applying direct heat, hammering, or dropping it. Heating or sudden shock creates misalignment of the molecules, causing the strength of the magnet to decrease. When a magnet is to be stored, devices known as keeper bars are installed to provide an easy path for flux lines from one pole to the other. This promotes the retention of the molecules in their north-south alignment. The presence of the magnetic force or field around a magnet can best be demonstrated by the experiment illustrated in Figure 12-17. A sheet of transparent material, such as glass or lucite trademark, is placed over a bar magnet and iron filings are sprinkled slowly on this transparent shield. If the glass or lucite trademark is tapped lightly, the iron filings arrange themselves in a definite pattern around the bar, forming a series of lines from the north to south end of the bar to indicate the pattern of the magnetic field. As shown, the field of a magnet is made up of many individual forces that appear as lines in the iron filing demonstration. Although they are not lines in the ordinary sense, this word is used to describe the individual nature of the separate forces making up the entire magnetic field. These lines of force are also referred to as magnetic flux. They are separate and individual forces, since one line will never cross another. Indeed, they actually repel one another. They remain parallel to one another and resemble stretched rubber bands, since they are held in place around the bar by the internal magnetizing force of the magnet. The demonstration with iron filings further shows that the magnetic field of a magnet is concentrated at the ends of the magnet. These areas of concentrated flux are called the north and south poles of the magnet. There is a limit to the number of lines of force that can be crowded into a magnet of a given size. When a magnetizing force is applied to a piece of magnetic material, a point is reached where no more lines of force can be induced or introduced. The material is then said to be saturated. The characteristics of the magnetic flux can be demonstrated by tracing the flux patterns of two bar magnets with like poles together. Figure 12-18. The two like poles repel one another because the lines of force will not cross each other. As the arrows on the individual lines indicate, the lines turn aside as the two like poles are brought near each other, and travel in a path parallel to each other. Lines moving in this manner repel each other, causing the magnets as a whole to repel each other. By reversing the position of one of the magnets, the attraction of unlike poles can be demonstrated. Figure 12-19. As the unlike poles are brought near each other, the lines of force rearrange their paths, and most of the flux leaving the north pole of one magnet enters the south pole of the other. The tendency of lines of force to repel each other is indicated by the bulging of the flux in the air gap between the two magnets. To further demonstrate that lines of force do not cross one another, a bar magnet and a horseshoe magnet can be positioned to display a magnetic field similar to that of figure 12-20. The magnetic fields of the two magnets do not combine, but are rearranged into a distorted flux pattern. The two bar magnets may be held in the hands, and the north poles brought near each other to demonstrate the force of repulsion between like poles. In a similar manner, the two south poles can demonstrate this force. The force of attraction between unlike poles can be felt by bringing a south and a north end together. Figure 12-21, 12-9. Tracing out a magnetic field by means of iron filings. Iron filings. Magnet. How the iron filings arrange themselves. Lewisite. Magnet. Figure 12-17. Tracing out a magnetic field with iron filings. Air gap. Air gap. SNNS. NSNS. Figure 12-18. Like poles repel. Figure 12-19. And like poles attract. 12-10. N. NS. SNSNSNSNSNSN. S. Figure 12-22. Magnetic poles in a broken magnet. Figure 12-20. Bypassing flux lines. Figure 12-22 illustrates another characteristic of magnets. If the bar magnet is cut or broken into pieces, each piece immediately becomes a magnet itself, with a north and south pole. This feature supports the theory that each molecule is a magnet, since each successive division of the magnet produces more magnets. Since the magnetic lines of force form a continuous loop, they form a magnetic circuit. It is impossible to say where in the magnet they originate or start. Arbitrarily, it is assumed that all lines of force leave the north pole of any magnet, and enter at the south pole. There is no known insulator for magnetic flux, or lines of force, since they pass through all materials. However, they do pass through some materials more easily than others. Thus, it is possible to shield items, such as instruments, from the effects of the flux by surrounding them with a material that offers an easier path for the lines of force. Figure 12-23 shows an instrument surrounded by a path of soft iron, which offers very little opposition to magnetic flux. The lines of force take the easier path, the path of greater permeability, and are guided away from the instrument. Materials such as soft iron and other ferrous metals are said to have a high permeability, the measure of the ease with which magnetic flux can penetrate a material. The permeability scale is based on a perfect vacuum with a rating of 1. Air and other non-magnetic materials are so close to this that they are also considered to have a rating. 33, 30, 27, 24, 0, 3, 6, 9. Radio compass. 21, 12, 15, 18. Soft iron. Figure 12-23. Magnetic shield. Of 1. The non-ferrous metals with a permeability greater than 1, such as nickel and cobalt, are called paramagnetic. The term ferromagnetic is applied to iron and its alloys, which have by far the greatest permeability. Any substance, such as bismuth, having a permeability of less than 1, is considered diamagnetic. SNNSNSSNSNSN. Repulsion attraction. Figure 12-21. Repulsion and attraction of magnet poles. 12-11. Reluctance, the measure of opposition to the lines of force through a material, can be compared to the resistance of an electrical circuit. The reluctance of soft iron, for instance, is much lower than that of air. Figure 12-24 demonstrates that a piece of soft iron placed near the field of a magnet can distort the lines of force, which follow the path of lowest reluctance through the soft iron. The magnetic circuit can be compared in many respects to an electrical circuit. The magnetomotive force, causing lines of force in the magnetic circuit, can be compared to the electromotive force, EMF, or electrical pressure of an electrical circuit. The magnetomotive force is measured in Gilberts, symbolized by the capital letter F. The symbol for the intensity of the lines of force, or flux, is the Greek letter phi, and the unit of field intensity is the Gauss. An individual line of force, called a Maxwell, in an area of 1 square centimeter produces a field intensity of 1 Gauss. Using reluctance rather than permeability, the law for magnetic circuits can be stated. A magnetomotive force of 1 Gilbert causes 1 Maxwell, or line of force, to be set up in a material, when the reluctance of the material is 1. Types of magnets. Magnets are either natural or artificial. Since naturally occurring magnets or lodestones have no practical use, all magnets considered in this chapter are artificial or man-made. Artificial magnets can be further classified as permanent magnets, which retain their magnetism long after the magnetizing force has been removed, and temporary magnets, which quickly lose most of their magnetism when the external magnetizing force is removed. Modern permanent magnets are made of special alloys that have been found through research to create increasingly better magnets. The most common categories of magnet materials are made out of aluminum, nickel, cobalt, alnicos, strontium iron, ferrites, also known as ceramics, neodymium iron boron, neomagnets, and samarium cobalt. Alnico, an alloy of iron, aluminum, nickel and cobalt, is considered one of the very best. Others with excellent magnetic qualities are alloys such as Vermalloy trademark and Permender trademark. The ability of a magnet to hold its magnetism varies greatly with the type of metal, and is known as retentivity. Magnets made of soft iron are very easily magnetized but quickly lose most of their magnetism when the external magnetizing force is removed. The small amount of magnetism remaining, called residual magnetism, is of great importance in such electrical applications as generator operation. Horseshoe magnets are commonly manufactured in 2 forms. Figure 12-25, the most common type is made from a long bar curved into a horseshoe shape, while a variation of this type consists of 2 bars connected by a 3rd bar, or yoke. Magnets can be made in many different shapes, such as balls, cylinders, or discs. One special type of magnet is the ring magnet, or Graham ring, often used in instruments. This is a closed-loop magnet, similar to the type used in transformer cores, and is the only type that has no poles. Sometimes special applications require that the field of force lie through the thickness rather than the length of a piece of metal. Such magnets are called flat magnets, and are used as pole pieces in generators and motors. Electromagnetism. In 1820, the Danish physicist, Hans Christian Ørsted, discovered that the needle of a compass brought near a current-carrying conductor would be deflected. When the current flow stopped, the compass needle returned to its original position. This important discovery demonstrated a relationship between electricity and magnetism that led to the electromagnet and to many of the inventions on which modern industry is based. Ørsted discovered that the magnetic field had no connection with the conductor in which the electrons were flowing, because the conductor was made of non-magnetic copper. The electrons moving through the wire created the magnetic field around the conductor. Since a magnetic field accompanies a N, SS, Sn, soft iron, Ns, N, S. Figure 12-25. 2 forms of horseshoe magnets. Figure 12-24. Effect of a magnetic substance in a magnetic field. 12-12. Charged particle. The greater the current flow, the greater the magnetic field. Figure 12-26 illustrates the magnetic field around a current-carrying wire. A series of concentric circles around the conductor represent the field, which if all the lines were shown would appear more as a continuous cylinder of such circles around the conductor. As long as current flows in the conductor, the lines of force remain around it. Figure 12-27. If a small current flows through the conductor, there will be a line of force extending out to circle A. If the current flow is increased, the line of force increases in size to circle B, and a further increase in current expands it to circle C. As the original line, circle, of force expands from circle A to B, a new line of force appears at circle A. As the current flow increases, the number of circles of force increases, expanding the outer circles farther from the surface of the current-carrying conductor. Conductor. A B. C. Magnetic lines. Figure 12-27. Expansion of magnetic field as current increases. Magnetic fields. Conductor. Figure 12-26. Magnetic field formed around a conductor in which current is flowing. If the current flow is a steady non-varying direct current, the magnetic field remains stationary. When the current stops, the magnetic field collapses and the magnetism around the conductor disappears. A compass needle is used to demonstrate the direction of the magnetic field around a current-carrying conductor. Figure 12-28a shows a compass needle positioned at right angles to, and approximately 1 inch from, a current-carrying conductor. If no current were flowing, the north-seeking end of the compass needle would point toward the Earth's magnetic pole. When current flows, the needle lines itself up at right angles to a radius drawn from the conductor. Since the compass needle is a small magnet, with lines of magnetic field. Checking direction of magnetic field. Using NS compass and left-hand rule. Compass. Current-carrying conductor. AB. Figure 12-28. Magnetic field around a current-carrying conductor. 12-13. Direction of field. Direction of current. Figure 12-29. Left-hand rule. Force extending from south to north inside the metal. It turns until the direction of these lines agrees with the direction of the lines of force around the conductor. As the compass needle is moved around the conductor, it maintains itself in a position at right angles to the conductor, indicating that the magnetic field around a current-carrying conductor is circular. As shown in figure 12-28b, when the direction of current flow through the conductor is reversed, the compass needle points in the opposite direction, indicating the magnetic field has reversed its direction. A method used to determine the direction of the lines of force when the direction of the current flow is known is shown in figure 12-29. If the conductor is grasped in the left hand, with the thumb pointing in the direction of current flow, the fingers will be wrapped around the conductor in the same direction as the lines of the magnetic field. This is called the left-hand rule. Although it has been stated that the lines of force have direction, this should not be construed to mean that the lines have motion in a circular direction around the conductor. Although the lines of force tend to act in a clockwise or counterclockwise direction, they are not revolving around the conductor. Since current flows from negative to positive, many illustrations indicate current direction with a dot symbol on the end of the conductor, when the electrons are flowing toward, and a plus sign when the current is flowing away from the observer. Figure 12-30. When a wire is bent into a loop, and an electric current flows through it, the left-hand rule remains valid. Figure 12-31. If the wire is coiled into two loops, many of the lines of force become large enough to include both loops. Lines of force go through the loops in the same direction, circle around the outside of the two coils, and come in at the opposite end. Figure 12-32. When a wire contains many such loops, it is called a coil. The lines of force form a pattern through all the loops, causing a high concentration of flux lines through the center of the coil. Figure 12-33. In a coil made from loops of a conductor, many of the lines of force are dissipated between the loops of the coil. By placing a soft iron bar inside the coil, the lines of force are concentrated in the center of the coil, since soft iron has a greater permeability than air. Figure 12-34. This combination of an iron core in a coil of wire loops, or turns, is called an electromagnet, since the poles, ends, of the coil possess the characteristics of a bar magnet. The addition of the soft iron core does two things for the current-carrying coil. First, the magnetic flux is increased. Second, the flux lines are more highly concentrated. When direct current flows through the coil, the core becomes magnetized with the same polarity, location of north and south poles, as the coil would have without the core. If the current is reversed, the polarity is also reversed. The polarity of the electromagnet is determined by the left-hand rule in the same manner as the polarity of the coil without the core was determined. If the coil is grasped in the left hand in such a manner that the fingers curve around the coil in the direction of electron flow, minus to plus, the thumb points in the direction of the north pole. Figure 12-35, plus. Dot indicates current is cross indicates current is flowing out of the conductor flowing into the conductor. Figure 12-31. Magnetic field around a looped conductor. Figure 12-30. Direction of current flow in a conductor. 12-14. Direction of current. Figure 12-32. Magnetic field around a conductor with two loops. SN. Figure 12-33. Magnetic field of a coil. SN. Figure 12-34. Electromagnet. 12-15. SN. Figure 12-35. Left-hand rule applied to a coil. The strength of the magnetic field of the electromagnet can be increased by either increasing the flow of current, or the number of loops in the wire. Doubling the current flow approximately doubles the strength of the field. In a similar manner, doubling the number of loops approximately doubles magnetic field strength. Finally, the type of metal in the core is a factor in the field strength of the electromagnet. A soft iron bar is attracted to either pole of a permanent magnet and, likewise, is attracted by a current-carrying coil. The lines of force extend through the soft iron, magnetizing it by induction, and pulling the iron bar toward the coil. If the bar is free to move, it is drawn into the coil to a position near the center, where the field is strongest. Figure 12-36. Electromagnets are used in electrical instruments, motors, generators, relays, and other devices. Some electromagnetic devices operate on the principle that an iron core held away from the center of a coil is rapidly pulled into a center position when the coil is energized. This principle is used in the solenoid, also called solenoid switch or relay, in which the iron core is spring-loaded off-center and moves to complete a circuit when the coil is energized. Conventional flow and electron flow. Today's technician will find that there are two competing schools of thought and analytical practices regarding the flow, NS, of electricity. The two are called the conventional current theory and the electron theory. Conventional flow. Of the two, the conventional current theory was the first to be developed and, through many years of use, this method has become ingrained in electrical texts. The theory was initially advanced by Benjamin Franklin, who reasoned that current flowed out of a positive source into a negative source or an area that lacked an abundance of charge. The notation assigned to the electric charges was positive, plus, for the abundance of charge and negative, dash, for a lack of charge. It then seemed natural to visualize the flow of current as being from the positive, plus, to the negative, dash, electron flow. Later discoveries were made that proved just the opposite is true. Electron flow is what actually happens when an abundance of electrons flow out of the negative, dash, source to an area that lacks electrons or the positive, plus, source. Both conventional flow and electron flow are used in industry. Many textbooks in current use employ both electron flow and conventional flow methods. From the practical standpoint of the technician troubleshooting a system, it makes little to no difference which way current is flowing as long as it is used consistently in the analysis. Electromotive force, voltage. Unlike current, which is easy to visualize as a flow, voltage is a variable that is determined between 2 points. Often, we refer to voltage as a value across 2 points. It is the electromotive force, EMF, or the push or pressure felt in a conductor that ultimately moves the electrons in a flow. The symbol for EMF is the capital letter E across the terminals of the typical aircraft battery. Voltage can be measured as the potential difference of 12 volts or 24 volts. That is to say that between the two terminal posts of the battery, there is an EMF of 12 or 24 volts available to push current through a circuit. Relatively free electrons in the negative terminal move toward the excessive number of positive charges in the positive terminal. Recall from the discussion on static electricity that like charges repel each other but opposite charges attract each other. The net result is a flow or current through a conductor. There cannot be a flow in a conductor unless there is an applied voltage from a battery, generator, or ground power unit. The potential difference, or the voltage across any 2 points in an electrical system, can be determined by Figure 12-36. Solenoid with iron core. 12-16. Where E equals Q. E equals potential difference in volts. C equals energy expanded or absorbed in joules. J. Q equals charge measured in coulombs. Figure 12-37 illustrates the flow of electrons of electric current. Two interconnected water tanks demonstrate that when a difference of pressure exists between the two tanks, water flows until the two tanks are equalized. The illustration shows the level of water in tank A to be at a higher level, reading 10 psi, higher potential energy, than the water level in tank B, reading 2 psi, lower potential energy. Between the two tanks, there is 8 psi potential difference. If the valve in the interconnecting line between the tanks is opened, water flows from tank A into tank B until the level of water, potential energy, of both tanks is equalized. It is important to note that it was not the pressure in tank A that caused the water to flow. Rather, it was the difference in pressure between tank A and tank B that caused the flow. This comparison illustrates the principle that electrons move, when a path is available, from a point of excess electrons, higher potential energy, to a point deficient in electrons, lower potential energy. The force that causes this movement is the potential difference in electrical energy between the 2 points. This force is called the electrical pressure, or the potential difference, or the electromotive force, electron moving force. Current. Electrons in motion make up an electric current. This electric current is usually referred to as current or current flow, no matter how many electrons are moving. Current is a measurement of a rate at which a charge flows through some region of space or a conductor. The moving charges are the free electrons found in conductors, such as copper, silver, aluminum, and gold. The term free electron describes a condition in some atoms where the outer electrons are loosely bound to their parent atom. These loosely bound electrons, a B, can be easily motivated to move in a given direction when an external source, such as a battery, is applied to the circuit. These electrons are attracted to the positive terminal of the battery, while the negative terminal is the source of the electrons. The greater amount of charge moving through the conductor in a given amount of time translates into a current. Charge current equals time, or Q equals T, where I equals current in amperes, AQ equals charge in coulombs. C. T equals time. The System International C. unit for current is the ampere, A, where C1A equals 1 S. 1 ampere, A of current is equivalent to 1 coulomb, C, of charge passing through a conductor in 1 second. 1 coulomb of charge equals 6.28 billion electrons. The symbol used to indicate current in formulas, or on schematics is the capital letter, I. When current flow is one direction, it is called direct current, DC. Later in the text, the form of current that periodically oscillates back and forth within the circuit is discussed. The present discussion is only concerned with the use of DC. The velocity of the charge is actually an average velocity, and is called drift velocity. To understand the idea of drift velocity, think of a conductor in which the charge carriers are free electrons. These electrons are always in a state of random motion similar to that of gas molecules. When a voltage is applied across the conductor, an EMF creates an electric field within the conductor and a current is established. The electrons do not move in a straight direction, but undergo repeated collisions with other nearby atoms. These collisions usually knock other free electrons from their atoms, and these electrons move on toward the positive end of the conductor with an average velocity called the drift velocity, which is relatively a slow speed. To understand the nearly instantaneous speed of the effect of the current, it is helpful to visualize a long tube filled with steel balls as shown in figure 12-38. It can be seen that a ball introduced in one end of the tube, which represents the conductor, will immediately cause a ball to be emitted at the opposite end of the tube. Figure 12-37. Difference of pressure. 12-17. 10 V. 20 ohms. Thus, electric current can be viewed as instantaneous, even though it is the result of a relatively slow drift of electrons. Ohm's law, resistance. The two fundamental properties of current and voltage are related by a third property known as resistance. In any electrical circuit, when voltage is applied to it, a current results. The resistance of the conductor determines the amount of current that flows under the given voltage. In most cases, the greater the circuit resistance, the less the current. If the resistance is reduced, then the current increases. This relation is linear in nature and is known as Ohm's law. By having a linearly proportional characteristic, it is meant that if one unit in the relationship increases or decreases by a certain percentage, the other variables in the relationship increase or decrease by the same percentage. An example would be if the voltage across a resistor is doubled, then the current through the resistor doubles. It should be added that this relationship is true only if the resistance in the circuit remains constant. If the resistance changes, current also changes. A graph of this relationship is shown in figure 12-39, which uses a constant resistance of 20 ohms. The relationship between voltage and current in this example shows voltage plotted horizontally along the x-axis in values from 0 to 120 volts, and the corresponding values of current are plotted vertically in values from 0 to 6.0 amperes along the y-axis. A straight line drawn through all the points where the voltage and current lines meet represents the equation I equals E/20 and is called a linear relationship. If E equals 10 V, then equals 0.5 A. If E equals 60 V, then equals 3 A. 20 ohms. If E equals 120 V, 120 V then equals 6 A. 20 ohms. Figure 12-38. Electron movement. Ohm's law may be expressed as an equation, as follows. Equation 1. EI equals R. I equals current in amperes, A equals voltage, V, R equals resistance, omega, where I is current in amperes, E is the potential difference measured in volts, and R is the resistance measured in ohms. If any two of these circuit quantities are known, the third may be found by simple algebraic transposition. With this equation, we can calculate current in a circuit if the voltage and resistance are known. This same formula can be used to calculate voltage. By multiplying both sides of the equation 1 by R, we get an equivalent form of Ohm's law, which is equation 2E equals I, R. Finally, if we divide equation 2 by I, we solve for resistance. This relationship is true only if the resistance in the circuit remains constant. If the resistance changes, current also changes. A graph of this relationship is shown in figure 12-39, which uses a constant resistance of 20 ohms. The relationship between voltage and current in this example shows voltage plotted horizontally along the x-axis in values from 0 to 120 volts. The corresponding values of current are plotted vertically in values from 0 to 6.0 amperes along the y-axis. A straight line drawn through all the points where the voltage and current lines meet represents the equation I equals E/20 and is called a linear relationship. Equation 3. ER equals I. All three formulas presented in this section are equivalent to each other, and are simply different ways of expressing Ohm's law. The various equations, which may be derived by transposing the basic law, can be easily obtained by using the triangles in figure 12-40. The triangles containing E, R, and I are divided into two parts, with E above the line, and I times R below it. To determine an unknown circuit quantity, when the other two are known, cover the unknown quantity with a thumb. The location of the remaining uncovered letters in the triangle indicate the mathematical operation to be performed. For example, 12-18. Amperes, I. 6.0, 5.5, 5.0, 4.5, 4.0, 3.5, 3.0, 2.5, 2.0, 1.5, 1.0, 0.5, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90 billion 100 million 110,120 volts. E, A, E, I, X, R. R equals 20 ohms, constant. B, E, I, X, R. Figure 12-39. Voltage versus current in a constant resistance circuit. C. Find I. Refer to figure 12-40A, and cover I with the thumb. The uncovered letters indicate that E is to be divided by R, where I equals E/R. To find R, refer to figure 12-40B, and cover R with the thumb. The result indicates that E is to be divided by I, or R equals E/I. To find D, refer to figure 12-40C, and cover E with the thumb. The result indicates I is to be multiplied by R, or E equals I times R. This chart is useful when learning to use Ohm's law. It should be used to supplement the beginner's knowledge of the algebraic method. Resistance of a conductor. While wire of any size or resistance value may be used, the word conductor usually refers to materials that offer low resistance to current flow, and the word insulator describes materials that offer high resistance to current. There is no distinct dividing line between conductors and insulators. Under the proper conditions, all types of material conduct some current. Materials offering a resistance to current flow midway between the best conductors and the poorest conductors, insulators, are sometimes referred to as semiconductors, and find their greatest application in the field of transistors. The best conductors are materials, chiefly metals, which possess a large number of free electrons. Conversely, insulators are materials having few free electrons. The best conductors are silver, copper, gold, and aluminum, but some non-metals, such as carbon and water, can be used as conductors. Materials such as rubber, glass, ceramics, and plastics are such poor conductors that they are usually used. To find I, amperes, place thumb over I and divide E by R as indicated. To find R, ohms, place thumb over R and divide as indicated. To find D, volts, place thumb over E and multiply as indicated. E, I, X, R. Figure 12-40. Ohm's law chart. As insulators, the current flow in some of these materials is so low that it is usually considered zero. The unit used to measure resistance is called the ohm. The symbol for the ohm is the Greek letter omega, omega. In mathematical formulas, the capital letter R refers to resistance. The resistance of a conductor and the voltage applied to it determine the number of amperes of current flowing through the conductor. Thus, 1 ohm of resistance limits the current flow to 1 ampere in a conductor to which a voltage of 1 volt is applied. Factors affecting resistance. 1. The resistance of a metallic conductor is dependent on the type of conductor material. It has been pointed out that certain metals are commonly used as conductors because of the large number of free electrons in their outer orbits. Copper is usually considered the best available conductor material, since a copper wire of a particular diameter offers a lower resistance to current flow than an aluminum wire of the same diameter. However, aluminum is much lighter than copper, and for this reason, as well as cost considerations, aluminum is often used when the weight factor is important. 12-19. 2. The resistance of a metallic conductor is directly proportional to its length. The longer the length of a given size of wire, the greater the resistance. Figure 12-41 shows two wire conductors of different lengths. If 1 volt of electrical pressure is applied across the two ends of the conductor that is 1 foot in length, and the resistance to the movement of free electrons is assumed to be 1 ohm, the current flow is limited to 1 ampere. If the same size conductor is doubled in length, the same electrons set in motion by the 1 volt applied now find twice the resistance. Consequently, the current flow is reduced by 1/2. 3. The resistance of a metallic conductor is inversely proportional to the cross-sectional area. This area may be triangular or even square, but is usually circular. If the cross-sectional area of a conductor is doubled, the resistance to current flow is reduced in half. This is true because of the increased area in which an electron can move without collision, or capture by an atom. Thus, the resistance varies inversely with the cross-sectional area of a conductor. 4. The fourth major factor influencing the resistance of a conductor is temperature. Although some substances, such as carbon, show a decrease in resistance as the ambient, surrounding, temperature increases, most materials used as conductors increase in resistance as temperature increases. The resistance of a few alloys, such as constantan and manganese trademark, change very little as the temperature changes. The amount of increase in the resistance of a 1 ohm sample of a conductor, per degree rise in temperature above 0 degrees centigrade, C, the assumed standard, is called the temperature coefficient of resistance. For each metal, this is a different value. For example, for copper the value is approximately 0.00427 ohm. Thus, a copper wire having a resistance 2 feet, 0.5 amp, 2 ohms, 1 foot, plus 1 amp, 1 ohm, of 50 ohms at a temperature of 0 degrees Celsius has an increase in resistance of 50 times 0.00427, or 0.214 ohm, for each degree rise in temperature above 0 degrees Celsius. The temperature coefficient of resistance must be considered where there is an appreciable change in temperature of a conductor during operation. Charts listing the temperature coefficient of resistance for different materials are available. Figure 12-42 shows a table for resistivity of some common electric conductors. The resistance of a material is determined by 4 properties: material, length, area, and temperature. The first 3 properties are related by the following equation at T equals 20 degrees Celsius. Room temperature, ρ times 1, R equals A, where R equals resistance in ohms, ρ equals resistivity of the material in circular mil minus ohms per foot, L equals length of the sample, and theta equals area in circular mils. Resistance and relation to wire sizing. Circular conductors, wires/cables, because it is known that the resistance of a conductor is directly proportional to its length, and if we are given the resistance of the unit length of wire, we can readily calculate the resistance of any length of wire of that particular material having the same diameter. Also, because it is known that the resistance of a conductor is inversely proportional to its cross-sectional area, and if we are given the resistance of a length of wire with unit cross-sectional area, we can calculate the resistance of a similar length of wire of the same material with any cross-sectional area. Therefore, if we know the resistance of a given conductor, we can calculate the resistance for any conductor of the same material at the same temperature. From the relationship, ρ times 1, R equals A, conductor material resistivity, ohm meters at 20 degrees Celsius, silver 1.64 times 10-8, copper 1.72 times 10-8, aluminum 2.83 times 10-8, tungsten 5.50 times 10-8, nickel 7.80 times 10-8, iron 12.0 times 10-8, constantan 49.0 times 10-8, nichrome 110 times 10-8. Figure 12-41. Resistance varies with length of conductor. Figure 12-42. Resistivity table. 12-20. It can also be written R1, 1A1 equals R2, 1, 2A2. If we have a conductor that is 1 meter, m, long with a cross-sectional area of 1 millimeters 2, and has a resistance of 0.017 ohm. What is the resistance of 50 meters of wire from the same material, but with a cross-sectional area of 0.25 millimeters 2? R1, 1A1 equals R2, 1, 2A2. 50 meters 1 millimeter 2. R2 equals 0.017 omega times equals 3.4 omega 1 meter 0.25 millimeters 2. While the C units are commonly used in the analysis of electric circuits, electrical conductors in North America are still being manufactured using the foot as the unit length and the mil 1/1000th of an inch as the unit of diameter. Before using the equation R equals ρ times L/R to calculate the resistance of a conductor of a given American wire gauge, size, the cross-minus sectional area in square meters must be determined using the conversion factor 1 mil equals 0.0254 millimeters. The most convenient unit of wire length is the foot. Using these standards, the unit of size is the mil foot. Thus, a wire has unit size if it has a diameter of 1 mil and length of 1 foot. In the case of using copper conductors, we are spared the task of tedious calculations by using a table as shown in figure 12-43. Note that cross-sectional dimensions listed on the table are such that each decrease of one gauge number equals a 25% increase in the cross-sectional area. Because of this, a decrease of 3 gauge numbers represents an increase in cross-sectional area of approximately 2.1. Likewise, change of 10 wire gauge numbers represents a 10.1 change in cross-sectional area. Also, by doubling the cross-sectional area of the conductor, the resistance is cut in half. A decrease of 3 wire gauge numbers cut the resistance of the conductor of a given length in half. Rectangular conductors. Bus bars. To compute the cross-sectional area of a conductor in square mils, the length in mils of one side is squared. In the case of a rectangular conductor, the length of one side is multiplied by the length of the other. For example, a common rectangular bus bar, large, special conductor, is 3/8 inch thick and 4 inches wide. The 3/8 inch thickness may be expressed as 0.375 inch. Since 1000 mils equal 1 inch, the width in inches can be converted to 4000 mils. The cross-sectional area of the rectangular conductor is found by converting 0.375 to mils. 375 mils times 4000 mils equals 1,500,000 square mils. A number diameter in mils ohms per 1000 foot. 0000 460.0 0.04901 0004009.6 0.06180 00364.8 0.07793 0324.9 0.09827 1289.3 0.1239 2257.6 0.1563 3229.4 0.1970 4204.3 0.2485 5181.9 0.3133 6162.0 0.3951 8128.5 0.6282 10101.9 0.9989 12 80.81 1.588 14 64.08 2.525 16 50.82 4.016 18 40.30 6.385 20 31.96 10.15 22 25.35 16.14 24 20.10 25.67 26 15.94 40.81 28 12.64 64.9 30 10.03 103.2 Figure 12-43 Conversion table. When using copper conductors, power and energy. Power in an electrical circuit. This section covers power in the DC circuit and energy consumption. Whether referring to mechanical or electrical systems, power is defined as the rate of energy consumption or conversion within that system. That is, the amount of energy used or converted in a given amount of time. From the scientific discipline of physics, the fundamental expression for power is E. P equals T, where P equals power measured in watts, W. E equals energy, E is a script E measured in joules, J, and T equals time measured in seconds. 12-21. The unit measurement for power is the watt, W, which refers to a rate of energy conversion of 1 joule, J/second. Therefore, the number of joules consumed in 1 second is equal to the number of watts. A simple example is given below. Suppose 300 joules of energy is consumed in 10 seconds. What would be the power in watts? Energy general formula P equals time 300 J. P equals 10 seconds. P equals 30 W. The watt is named for James Watt, the inventor of the steam engine. Watt devised an experiment to measure the power of a horse in order to find a means of measuring the mechanical power of his steam engine. 1 horsepower is required to move 33,000 pounds 1 foot in 1 minute. Since power is the rate of doing work, it is equivalent to the work divided by time. Stated as a formula, this is 33,000 foot minus pounds power equals 60 seconds. P equals 550 foot-pounds/s. Electrical power can be rated in a similar manner. For example, an electric motor rated as a 1 horsepower motor requires 746 watts of electrical energy. Power formulas used in the study of electricity. When current flows through a resistive circuit, energy is dissipated in the form of heat. Recall that voltage can be expressed in the terms of energy and charge as given in the expression E equals Q, where E equals potential difference in volts, C equals energy expanded or absorbed in joules, J. Q equals charge measured in coulombs. Current I can also be expressed in terms of charge and time as given by the expression charge current equals time, or Q equals T, where I equals current in amperes, AQ equals charge in coulombs, C, T equals time. When voltage W/Q and current Q/T are multiplied, the charge Q is divided out, leaving the basic expression from physics, E times I equals Q times equals power TT. For a simple DC electrical system, Power dissipation can then be given by the equation. General power formula P equals I, E, where P equals power, I equals current, E equals volts. If a circuit has a known voltage of 24 volts and a current of 2 amps, then the power in the circuit is P equals I, E, P equals 2A, 24V, P equals 48W. Now recall Ohm's laws that state E equals I, R. If we now substitute IR for E in the general formula, we get a formula that uses only current I and resistance R to determine the power in a circuit. P equals I, IR, second form of power equation. P equals I2R. If a circuit has a known current of 2 amps and a resistance of 100 ohms, then the power in the circuit is P equals I2R. P equals 2A, 2100 ohms, P equals 400W. Using Ohm's law, which can be stated as I equals E/R, we can again make a substitution such that power can be determined by knowing only the voltage, E, and resistance, R, of the circuit. EP equals ER. 12-22. Third form of power equation E2. P equals R. If a circuit has a known voltage of 24 volts and a resistance of 20 ohms, then the power in the circuit is E2. P equals R. 24V, 2. P equals 20 ohms. P equals 28.8 W. Power in a series and parallel circuit. The total power dissipated in both a series and parallel circuit is equal to the sum of the power dissipated in each resistor in the circuit. Power is simply additive and can be stated as PT equals P1 plus P2 plus P3 plus Pn. Figure 12-44 provides a summary of all the possible transpositions of the Ohm's law formula and the power formula. Energy in an electrical circuit. Energy is defined as the ability to do work. Because power is the rate of energy usage, power use over a span of time is actually energy consumption. If power and time are multiplied together, we get energy. A joule is defined as a unit of energy. There is another unit of measure which is perhaps more familiar. Because power is expressed in watts and time in seconds, a unit of energy. E2. R. E. R. I2R. P. E. I. P. R. P. I. E. R. P. R. E. I. P. I. E2. P. I. R. I2P. Figure 12-44. Ohm's law formula can be called a watt-second, WS, or more recognizable from the electric bill, a kilowatt-hour, kilowatts per hour. Refer to Chapter 5, Physics, for further discussion on energy. Sources of electricity. Electrical energy can be produced in a number of methods. The four most common are pressure, chemical, thermal, and light. Pressure source. This form of electrical generation is commonly known as piezoelectric, piezo or pies taken from Greek. To press, pressure. To squeeze, is a result of the application of mechanical pressure on a dielectric or non-conducting crystal. The most common piezoelectric materials used today are crystalline quartz and Rochelle salt. However, Rochelle salt is being superseded by other materials, such as barium titanate. The application of a mechanical stress produces an electric polarization, which is proportional to this stress. This polarization establishes a voltage across the crystal. If a circuit is connected across the crystal, a flow of current can be observed when the crystal is loaded. Pressure is applied. An opposite condition can occur, where an application of a voltage between certain phases of the crystal can produce a mechanical distortion. This effect is commonly referred to as the piezoelectric effect. Piezoelectric materials are used extensively in transducers for converting a mechanical strain into an electrical signal. Such devices include microphones, phonograph pickups, and vibration sensing elements. The opposite effect, in which a mechanical output is derived from an electrical signal input, is also widely used in headphones and loudspeakers. Chemical source. Chemical energy can be converted into electricity. The most common form of this is the battery. A primary battery produces electricity using two different metals in a chemical solution like alkaline electrolyte, where a chemical reaction between the metals and the chemicals frees more electrons in one metal than in the other. One terminal of the battery is attached to one of the metals, such as zinc. The other terminal is attached to the other metal, such as manganese oxide. The end that frees more electrons develops a positive charge, and the other end develops a negative charge. If a wire is attached from one end of the battery to the other, electrons flow through the wire to balance the electrical charge. Thermal sources. The most common source of thermal electricity found in the aviation industry comes from thermocouples. Thermocouples are widely used as temperature sensors. They are cheap and interchangeable, have standard connectors, and can 12-23 measure a wide range of temperatures. Thermocouples are pairs of dissimilar metal wires joined at least at one end, which generate a voltage between the two wires that is proportional to the temperature at the junction. This is called the Seebeck effect. In honor of Thomas Seebeck, who first noticed the phenomena in 1821. It was also noticed that different metal combinations have a different voltage difference. Thermocouples are used to measure cylinder head temperatures and turbine inlet temperature, TIT. Light sources. A solar cell or a photovoltaic cell is a device that converts light energy into electricity. Fundamentally, the device contains certain chemical elements that, when exposed to light energy, release electrons. Photons and sunlight are taken in by the solar panel or cell, where they are absorbed by semiconducting materials, such as silicon. Electrons in the cell are broken loose from their atoms, allowing them to flow through the material to produce electricity. The complementary positive charges that are also created are called holes, absence of electron, and flow in the direction opposite of the electrons in a silicon solar panel. Solar cells have many applications, and have historically been used in Earth-orbiting satellites or space probes, handheld calculators, and wristwatches. Schematic representation of electrical components. The schematic is the most common place where the technician finds electronic symbols. The schematic is a diagram that depicts the interconnection and logic of an electronic or electrical circuit. Many symbols are employed for use in the schematic drawings, blueprints, and illustrations. This section briefly outlines some of the more common symbols and explains how to interpret them. Conductors. The schematic depiction of a conductor is simple enough. This is generally shown as a solid line. However, the line types may vary depending on who drew the schematics and what exactly the line represents. While the solid line is used to depict the wire or conductor, schematics used for aircraft modifications can also use other line types, such as a dash to represent existing wires prior to modification and solid lines for new wires. There are two methods employed to show wire crossovers and wire connections. Figure 12-45 shows the two methods of drawing wires that cross, version A and version B. Figure 12-46 shows the two methods for drawing wire that connect version A and version B. If version A in Figure 12-45 is used to depict crossovers, then version A for wire connections in Figure 12-46 is used. The same can then be said about the use of version B methods. The technician encounters both in common use. Figure 12-47 shows a few examples of the more common wire types that the technician encounters in schematics. They are the single wire, single shielded twisted pair or double, and the shielded triple. This is not an exhaustive list of wire types, but a fair representation of how they are depicted. Figure 12-47 also shows the wires having a wire number. These are shown for the sake of illustration, and vary from one installation agency to another. For further understanding of a wire numbering system, consult the appropriate wiring guide published by the agency that drew the prints. Regardless of AB. Figure 12-45. Unconnected crossover wires. AB. Figure 12-46. Connected wires. Typical wire No. SX001822. Single wire. 12 PB501-APJ356. Conductor. NM200A22. RF300A22. Shielded single wire. Shielded double wire. Shielded triple wire. Shielding. Figure 12-47. Common wire types. 12-24. The specifics of the wire numbering system. Organizations that exercise professional wiring practices have the installed wire marked in some manner. This is an aid to the technician who has to troubleshoot or modify the system at a later date. Types of resistors. Fixed resistor. Fixed resistors have built into the design a means of opposing current. Figure 12-48. The general use of a resistor in a circuit is to limit the amount of current flow. There are a number of methods used in construction and sizing of the resistor that control properties, such as resistance value, the precision of the resistance value, and the ability to dissipate heat. While in some applications the purpose of the resistive element is used to generate heat, such as in propeller and the ice boots, heat typically is the unwanted loss of energy. Carbon composition. The carbon-composed resistor is constructed from a mixture of finely grouped carbon/graphite, an insulation material for filler, and a substance for binding the material together. The amount of graphite in relation to the insulation material determines the ohmic or resistive value of the resistor. This mixture is compressed into a rod, which is fitted with axial leads or pigtails. The finished product is sealed in an insulating coating for isolation and physical protection. There are other types of fixed resistors in common use. Included in this group are carbon film, metal oxide, not extremely critical. For many uses, the actual resistance in ohms can be 20% higher or lower than the value marked on the resistor without causing difficulty. The percentage variation between the marked value and the actual value of a resistor is known as the tolerance of the resistor. The resistor coded for a 5% tolerance is not more than 5% higher or lower than the value indicated by the color code. The resistor color code is made up of a group of colors, numbers, and tolerance values. Each color is represented by a number, and in most cases, by a tolerance value. Figure 12-49, when the color code is used with the end-to-center band marking system, the resistor is normally marked with bands of color at one end of the resistor. The body or base color of the resistor has nothing to do with the color code, and in no way indicates a resistance value. To prevent confusion, this body is never the same color as any of the bands indicating resistance value. Color band decoding. When the end-to-center band marking system is used, either 3 or 4 bands mark the resistor. 1. The first color band, nearest the end of the resistor, indicates the first digit in the numerical resistance value. This band is never gold or silver in color. 2. The second color band always indicates the second digit of ohmic value. It is never gold or silver in color. Figure 12-50, resistor color code color number tolerance. 3. The third color band indicates the number of zeros to be added to the 2 digits derived from the first and second bands. Except in the following 2 cases: metal film, metal glaze. The construction of a film resistor is accomplished by depositing a resistive material evenly on a ceramic rod. This resistive material can be graphite for the carbon film resistor, nickel chromium for the metal film resistor, metal and glass for the metal glaze resistor, and metal and an insulating oxide for the metal oxide resistor. Resistor ratings: black 0, brown 1, 1% red 2, 2% orange 3, 3% yellow 4, 4% green 5, 5% blue 6, 6% violet 7, 7% gray 8, 8% white 9, 9% gold, 5% silver, 10% no color, 20%. Color code. It is very difficult to manufacture a resistor to an exact standard of ohmic values. Fortunately, most circuit requirements are. Figure 12-49. Resistor color code. Figure 12-48. Fixed resistor schematic. 12-25. A. If the third band is gold in color, the first 2 digits must be multiplied by 10%. B. If the third band is silver in color, the first 2 digits must be multiplied by 1%. 4. If there is a fourth color band, it is used as a multiplier for a percentage of tolerance, as indicated in the color code chart in Figure 12-49. If there is no fourth band, the tolerance is understood to be 20%. Figure 12-50 illustrates the rules for reading the resistance value of a resistor marked with the end-to-center band system. This resistor is marked with 3 bands of color, which must be read from the end toward the center. There is no fourth color band. Therefore, the tolerance is understood to be 20%. 20% of 250,000 omega equals 50,000 omega. Since the 20% tolerance is plus or minus, maximum resistance equals 250,000 omega plus 50,000 omega equals 300,000 omega. Minimum resistance equals 250,000 omega minus 50,000 omega equals 200,000 omega. The following paragraphs provide a few extra examples of resistor color band decoding. Figure 12-51 contains a resistor with another set of colors. This resistor code should be read as follows. The resistance of this resistor is 86,000 plus minus 10% ohms. The maximum resistance is 94,600 ohms, and the minimum resistance is 77,400 ohms. Another example is the resistance of the resistor in Figure 12-52 is 960 plus minus 5% ohms. The maximum resistance is 1008 ohms, and the minimum resistance is 912 ohms. Gray, blue, orange, silver. 8, 6, 0, 0, 0, 10%. Figure 12-51. Resistor color code example. White, blue, brown, gold. 960, 5%. Figure 12-52. Resistor color code example. Sometimes circuit considerations dictate that the tolerance must be smaller than 20%. Figure 12-53 shows an example of a resistor with a 2% tolerance. The resistance value of this resistor is 2,500 plus minus 2% ohms. The maximum resistance is 2,550 ohms, and the minimum resistance is 2,450 ohms. Figure 12-54 contains an example of a resistor with a black third color band. The color code value of black is 0, and the third band indicates the number of zeros to be added to the first 2 digits. In this case, a 0 number of zeros must be added to the first 2 digits. Therefore, no zeros are added. Thus, the resistance value is 10 plus minus 1% ohms. The maximum resistance is 10.1 ohms, and the minimum resistance is 9.9 ohms. There are two exceptions to the rule stating the third color band indicates the number of zeros. The first of these exceptions. Red. Green, red, red. First band. Second band, third band. Red, green, yellow. Color numerical valve significance first band. Red 2. First digit second band. Green 5. Second digit third band. Yellow 4 no. Of zeros to add. 2. 500 2%. Figure 12-53. Resistor with 2% tolerance. Brown. Black, black, brown. 1. 0. 1%. Figure 12-50. And 2 center band marking. Figure 12-54. Resistor with black third color band. 12-26. Is illustrated in figure 12-55. When the third band is gold in color, it indicates that the first two digits must be multiplied by 10%. The value of this resistor in this case is 10 times 0.10 plus minus sign 2% equals 1 equals 0.02 ohms. When the third band is silver, as is the case in figure 12-56, the first two digits must be multiplied by 1%. The value of the resistor is 0.45 plus minus sign 10% ohms. Wire wound. Wire-wound resistors typically control large amounts of current and have high power ratings. Resistors of this type are constructed by winding a resistance wire around an insulating rod usually made of porcelain. The windings are coated with an insulation material for physical protection and heat conduction. Both ends of the windings are connected to terminals, which are used to connect the resistor to a circuit. Figure 12-57. A wire-wound resistor with cap is a special type of fixed resistor that can be adjusted. These adjustments can be made by moving a slide bar tap or by moving the tap to a preset incremental position. While the tap may be adjustable, the adjustments are usually set at the time of installation to a specific value and then operated in service as a fixed resistor. Another type of wire-wound resistor is constructed of manganese wire, used when high precision is needed. Brown. Black, gold, multiplier, red. 1. 0 10% 2%. Figure 12-55. Resistor with gold third band. Yellow. Green, silver, multiplier, silver. 4. 5 1% 10%. Variable resistors. Variable resistors are constructed so that the resistive value can be changed easily. This adjustment can be manual or automatic, and the adjustments can be made while the system that it is connected to is in operation. There are two basic types of manual adjusters: the rheostat and the potentiometer. Rheostat. A rheostat is a variable resistor used to vary the amount of current flowing in a circuit. Figure 12-58. Figure 12-59 shows a rheostat connected in series with an ordinary resistance in the series circuit. As the slider arm moves from point A to B, the amount of rheostat resistance, AB, is increased. Since the rheostat resistance and the fixed resistance are in series, the total resistance in the circuit also increases, and the current in the circuit decreases. On the other hand, if the slider arm is moved toward point A, the total resistance decreases and the current in the circuit increases. Potentiometer. The potentiometer is considered a three-terminal device. Figure 12-60, as illustrated. Terminals 1 and 2 have the entire value of the potentiometer resistance between them. Terminal 3 is the wiper or moving contact. Through this wiper, the resistance between terminals 1 and 3 or terminals 2 and 3 can be varied. While the rheostat is used to vary the current in a circuit, the potentiometer is used to vary the voltage in a circuit. A typical use for this component can be found in the volume controls on an audio panel and input devices for flight data recorders, among many other applications. In figure 12-61A, a potentiometer is used to obtain a variable voltage from a fixed voltage source to apply to an electrical load. The voltage applied to the load is the voltage between points 2 and 3. When the slider arm is moved to point 1, the entire voltage is applied to the electrical device load. When the arm is moved to point 3, the voltage applied to the load is 0. The potentiometer makes possible the application of any voltage between 0 and full voltage to the load. The current flowing through the circuit of figure 12-61 leaves the negative terminal electron flow of the battery and divides one part flowing through the lower portion of the figure 12-56. Resistor with a silver third band. Figure 12-57. Wire-wound resistors. Figure 12-58. Rheostat schematic symbol. 12-27. PA. 1. 2. Load. 3. Figure 12-59. Rheostat connected in series. 1. A. Terminals. 3. Shaft. Wiper. 2. Figure 12-60. Potentiometer schematic symbol. Potentiometer. Points 3 to 2, and the other part through the load. Both parts combine at point 2 and flow through the upper portion of the potentiometer, points 2 to 1, back to the positive terminal of the battery. In view B of figure 12-61, a potentiometer and its schematic symbol are shown. In choosing a potentiometer resistance, the amount of current drawn by the load should be considered, as well as the current flow through the potentiometer at all settings of the slider arm. The energy of the current through the potentiometer is dissipated in the form of heat. It is important to keep this wasted current as small as possible by making the resistance of the potentiometer as large as practicable. In most cases, the resistance of the potentiometer can be several times the resistance of the load. Figure 12-62 shows how a potentiometer can be wired to function as a rheostat. Linear potentiometers. In a linear potentiometer, the resistance between both terminal and the wiper varies linearly with the position of the wiper. To illustrate, 1/4 of a turn on the potentiometer results in 1/4 of the total resistance. The same relationship exists when 1/2, or 3/4 of potentiometer movement. Figure 12-63, resistive strip. Rotary potentiometer construction. B. Figure 12-61. Potentiometer and schematic symbol. 1. 3. 2. Figure 12-62. Potentiometer wired to function as rheostat. 100 ohms, 70 ohms, 30 ohms. A. 25%. 100 ohms, 30 ohms, 70 ohms. B. 50%. 100 ohms, 10 ohms, 90 ohms. C. 75%. Figure 12-63. Linear potentiometer schematic. 12-28. Tapered potentiometers. Resistance varies in a nonlinear manner in the case of the tapered potentiometer. Figure 12-64. Keep in mind that 1/2 of full potentiometer travel does not necessarily correspond to 1/2 the total resistance of the potentiometer. Thermistors. The thermistor is a type of a variable resistor that is temperature sensitive. Figure 12-65. This component has a negative temperature coefficient, which means that as the sensed temperature increases, the resistance of the thermistor decreases. Photoconductive cells. The photoconductive cell is similar to the thermistor. Like the thermistor, it has a negative temperature coefficient. Unlike the thermistor, the resistance is controlled by light intensity. This kind of component can be found in radio control heads, where the intensity of the ambient light is sensed through the photoconductive cell, resulting in the backlighting of the control heads to adjust to the flight deck lighting conditions. Figure 12-66. Circuit protection devices. Perhaps the most serious trouble in a circuit is a direct short. The term direct short describes a situation in which some point in the circuit, where full system voltage is present, comes in direct contact with the ground, or return side of the circuit. This establishes a path for current flow that contains no resistance other than that present in the wires carrying the current, and these wires have very little resistance. Figure 12-66. Photoconductive cell schematic symbol component. 100 ohms, 70 ohms, 30 ohms. A. 25%. 100 ohms, 30 ohms, 70 ohms. B. 50%. 100 ohms, 10 ohms, 90 ohms. C. 75%. Figure 12-64. Tapered potentiometer. T. Most wires used in aircraft electrical circuits are small gauge, and their current carrying capacity is quite limited. The size of the wires used in any given circuit is determined by the amount of current the wires are expected to carry under normal operating conditions. Any current flow in excess of normal, such as the case of a direct short, would cause a rapid generation of heat. If the excessive current flow caused by the short is left unchecked, the heat in the wire could cause a portion of the wire to melt and at the very least, open the circuit. To protect aircraft electrical systems from damage and failure caused by excessive current, several kinds of protective devices are installed in the systems. Fuses, circuit breakers, thermal protectors, and arc fault circuit breakers are used for this purpose. Circuit protective devices, as the name implies, all have a common purpose: to protect the units and the wires in the circuit. Some are designed primarily to protect the wiring, and to open the circuit in such a way as to stop the current flow when the current becomes greater than the wires can safely carry. Other devices are designed to protect the unit in the circuit by stopping the current flow to it when the unit becomes excessively warm. Fuses are used to protect the circuit from overcurrent conditions. Figure 12-67. The fuse is installed in the circuit so that all the current in the circuit passes through it. In most fuses, the strip of metal is made of an alloy of tin and bismuth, which melts and opens the circuit when the current exceeds the rated capacity of the fuse. For example, if a 5 amp fuse is placed into a circuit, the fuse allows currents up to 5 amps to pass. Because the fuse is intended to protect the circuit, it is quite important that its capacity match the needs of the circuit in which it is used. Figure 12-65. Schematic symbol for thermistor. 12-29. Figure 12-67. Schematic symbol for fuse. When replacing a fuse, consult the applicable manufacturer's instructions to be sure a fuse of the correct type and capacity is installed. Fuses are installed in two types of fuse holders in aircraft. Plug-in holders, or inline holders, are used for small and low-capacity fuses. Clip-type holders are used for heavy high-capacity fuses and current limiters. Current limiter. The current limiter is very much like the fuse. However, the current limiter link is usually made of copper, and will stand a considerable overload for a short period of time. Like the fuse, it opens up in an overcurrent condition in heavy current circuits such as 30 amp or greater. These are used primarily to sectionalize an aircraft circuit or bus. Once the limiter is opened, it must be replaced. The schematic symbol for the current limiter is the same as that for the fuse. Circuit breaker. The circuit breaker is commonly used in place of a fuse and is designed to break the circuit and stop the current flow when the current exceeds a predetermined value. Unlike the fuse, the circuit breaker can be reset, whereas the fuse or current limiter must be replaced. Figure 12-68. There are several types of circuit breakers in general use in aircraft systems. One is a magnetic type. When excessive current flows in the circuit, it makes an electromagnet strong enough to move a small armature, which trips the breaker. Figure 12-68. Schematic symbol for circuit breaker. Another type is the thermal overload switch or breaker. This consists of a bimetallic strip which, when it becomes overheated from excessive current, bends away from a catch on the switch lever, and permits the switch to trip open. Most circuit breakers must be reset by hand. If the overload condition still exists, the circuit breaker trips again to prevent damage to the circuit. At this point, it is usually not advisable to continue resetting the circuit breaker, but to initiate troubleshooting to determine the cause. Repeated resetting of a circuit breaker can lead to circuit or component damage or worse. The possibility of a fire or explosion. Automatic reset type circuit breakers are not allowed in aircraft. Circuit breakers are commonly grouped on a circuit breaker panel that is accessible to the flight crew. Figure 12-69 shows a circuit breaker and a circuit breaker panel. Arc fault circuit breaker. In recent years, the arc fault circuit breaker has begun to provide an additional layer of protection beyond that of the thermal protection already provided by conventional circuit breakers. The arc fault circuit breaker monitors the circuit for an electrical arcing signature, which can indicate possible wiring faults and unsafe conditions. These conditions can lead to fires or loss of power to critical systems. The arc fault circuit breaker is only beginning to make an appearance in the aircraft industry, and is not widely used like the thermal type of circuit breaker. Thermal protectors. A thermal protector, or switch, is used to protect a motor. It is designed to open the circuit automatically whenever the temperature of the motor becomes excessively high. It has two positions, opened and closed. The most common use for a thermal switch is to keep a motor from overheating. If a malfunction in the motor causes it to overheat, the thermal switch breaks the circuit intermittently. The thermal switch contains a bimetallic disc, or strip, that bends and breaks the circuit when it is heated. This occurs because one of the metals expands more than the other when they are subjected to the same temperature. When the strip or disc cools, the metals contract and the strip returns to its original position and closes the circuit. Control devices. Components in the electrical circuits are typically not all intended to operate continuously or automatically. Most of them are meant to operate at certain times, under certain conditions, to perform very definite functions. There must be some means of controlling their operation. Either a switch, or a relay, or both may be included in the circuit for this purpose. 12-30. Figure 12-69. Circuit breaker assembly for aircraft electrical system. Switches. Switches control the current flow in most aircraft electrical circuits. A switch is used to start, to stop, or to change the direction of the current flow in the circuit. The switch in. Each circuit must be able to carry the normal current of the circuit, and must be insulated heavily enough for the voltage of the circuit. Figure 12-70 shows various switches used in aircraft electrical systems. An understanding of some basic definitions of the switch is necessary before any of the switch types are discussed. The number of poles, throws, and positions they have designates toggle switches, as well as some other type of switches. Pole. The switch is movable blade or contactor. The number of poles is equal to the number of circuits, or paths for current flow, that can be completed through the switch at any one time. Throw indicates the number of circuits, or paths for current, that it is possible to complete through the switch with each pole or contactor. Positions indicates the number of places at which the operating device, toggle, plunger, and so forth, comes to rest and at the same time open or close one or more circuits. Toggle switch. Single pole. Single throw, SPST, the single pole. Single throw, SPST switch allows a connection between two contacts. One of two conditions exist. Either the circuit is open in one position, or closed in the other position. Figure 12-71, single pole, double throw, SPDT, the single pole, double throw, SPDT, switch is shown in figure 12-72. With this switch, contact between one contact can be made between one contact and the other. Double pole, single throw, DPST, the double pole, single throw, DPST switch connection can be made between one set of contacts, and either of two other sets of contacts. Figure 12-73, Figure 12-70. Various types of switches used in modern aircraft. 12-31. Figure 12-71. Single pole, single throw switch schematic symbol. Figure 12-72. Single pole, double throw switch schematic symbol. Double pole, double throw, DPDT, the schematic symbol for the double pole, double throw, DPDT, switch is shown in figure 12-74. This type of switch makes a connection from one set of contacts to either of two other sets of contacts. A toggle switch that is spring-loaded to the off position, and must be held in the on position to complete the circuit is a momentary contact two-position switch. One that comes to rest at either of two positions, opening the circuit in one. Figure 12-73. Double pole, single throw switch schematic symbol. Figure 12-74. Double pole, double throw switch schematic symbol. Position and closing it in another is a two-position switch. A toggle switch that comes to rest at any one of three positions is a three-position switch. A switch that stays open, except when it is held in the closed position, is a normally open switch, usually identified as no. One that stays closed, except when it is held in the open position is a normally closed switch, North Carolina. Both kinds are spring-loaded to their normal position, and return to that position as soon as they are released. Locking toggles require the operator to pull out on the switch toggle before moving it into another position. Once in a new position, the switch toggle is released back into a lock, which then prevents the switch from inadvertently being moved. Microswitches. A microswitch opens or closes a circuit with a very small movement of the tripping device, 1/16 inch or less. This is what gives the switch its name. Since micro means small, microswitches are usually push-button switches. They are used primarily as limit switches to provide automatic control. 12-32. Operating plunger. Stationary contact. Movable contact. Grooved anchor 3-bladed spring. Figure 12-75. Cross-section of a microswitch. Of landing gears, actuator motors, and the like. Figure 12-75 shows a normally closed microswitch in cross-section and illustrates how these switches operate. When the operating plunger is pressed in, the spring and the movable contact are pushed, opening the contacts and the circuit. Figure 12-76 shows a push-button microswitch. Rotary selector switches. A rotary selector switch takes the place of several switches. When the knob of the switch is rotated, the switch opens one circuit and closes another. Ignition switches and voltmeter selector switches are typical examples of this kind of switch. Figure 12-77. Push-button switches. Push-button switches have one stationary contact and one movable contact. The movable contact is attached to the push-button. The push-button is either an insulator itself or is insulated from the contact. This switch is spring-loaded and designed for momentary contact. Lighted push-button switches. Another more common switch found in today's aircraft is the lighted push-button switch. This type of switch takes the Figure 12-77. Rotary switches. Form of a 5/8 inch to 1 inch cube with incandescent or LED lights to indicate the function of the switch. Switch designs come in a number of configurations. The two most common are the alternate action and momentary action, and usually have a 2-pole or 4-pole switch body. Other less common switch actions are the alternate and momentary holding coil configurations. The less known holding or latching coil switch bodies are designed to have a magnetic coil inside the switch body that is energized through two contacts in the base of the switch. When the coil is energized and the switch is pressed, the switch contacts remain latched until power is removed from the coil. This type of design allows for some degree of remote control over the switch body. Figure 12-78. The display optics of the lighted push-button switch provide the crew with a clear message that is visible under a wide range of lighting conditions with very high luminance and wide viewing angles. While some displays are simply a transparent screen that is backlit by an incandescent light, the higher quality and more reliable switches are available in sunlight-readable displays and night vision, NVIS, versions. Due to the sunlight environment of the flight deck, displays utilizing standard lighting techniques wash out when viewed in direct sunlight. Sunlight-readable displays are designed to minimize this effect. Figure 12-76. Push-button microswitch. 12-33. A. Figure 12-78. Lighted push-button switches. Lighted push-button switches can also be used in applications where a switch is not required and the optics are only for indications. This type of an indicator is commonly called an annunciator. Dual inline parallel, DIP, switches. The acronym DIP switch is defined as dual inline parallel switch in reference to the physical layout. DIP switches are commonly found in card cages and line replaceable units, LRU, and are used in most cases to adjust gains, control configurations, and so forth. Each one of the switches is generally an SPST slide or rocker switch. The technician may find this switch in packages ranging in size from DIP2 through DIP32. Some of the more common sizes are DIP4 and DIP8. Switch guards. Switch guards are covers that protect a switch from unintended operation. Prior to the operation of the switch, the guard is usually lifted. Switch guards are commonly found on systems such as fire suppression and override logics for various systems. Figure 12-79A shows a traditional switch with a guard, while Figure 12-79B shows a push-button switch with a guard. The guard needs to be moved before the switch can be pushed. Relays. A relay is simply an electromechanical switch, where a small amount of current can control a large amount of current. Figure 12-80. When a voltage is applied to the coil of the relay, the electromagnet is energized due to the current. When energized, an electromagnetic field pulls the common C or arm of the relay down. When the arm or common is pulled down, the circuit between the arm and the normally closed North Carolina contacts is opened and the circuit between the arm and the normally open No contacts are closed. When the energizing voltage is removed, the spring returns the arm contacts back to the normally closed North Carolina contacts. The relay usually has two connections for the coil. The plus side is designated as X1 and the ground side of the coil is designated as X2. B. Figure 12-79. A red guarded switch. B. Push-button switch with a guard. Series DC circuits. The series circuit is the most basic electrical circuit and provides a good introduction to basic circuit analysis. The series circuit represents the first building block for all of the circuits to be studied and analyzed. Figure 12-81 shows this simple circuit with nothing more than a voltage source or battery, a conductor, and a resistor. This is classified as a series circuit because the components are connected end-to-end, so that the same current flows through each component equally. There is only one path for the current to take and the battery and resistor are in series with each other. Next is to make a few additions to the simple circuit in Figure 12-81. 12-34. Multiple poles. B3. B1. B2. North Carolina No. C. A3. A1. A2. North Carolina No. C. X1. X1. X2. X2. Schematic symbol for a relay. Normally closed, North Carolina. Normally open, No. Common, C or arm. Electromagnet pulls contact down. N. X1. Plus, magnetic field. S. X2. Dash. Relay illustration. Figure 12-80. Basic relay. Plus. Dash. Figure 12-81. Simple DC circuit. Figure 12-82 shows an additional resistor and a little more detail regarding the values. With these values, we can now begin to learn more about the nature of the circuit. In this configuration, there is a 12-volt DC source in series with two resistors. R1 equals 10 ohms and R2 equals 30 ohms. For resistors in a series configuration, the total resistance of the circuit is equal to the sum of the individual resistors. The basic formula is RT equals R1 plus R2 plus R3 plus Rn. For Figure 12-82, this will be RT equals 10 ohms plus 30 ohms RT equals 40 ohms. Now that the total resistance of the circuit is known, the current for the circuit can be determined. In a series circuit, the current cannot be different at different points within the circuit. The current through a series circuit is always the same through each element and at any point. Therefore, the current in the simple circuit can now be determined using Ohm's law formula. E equals I, R. E solved for current, I equals R. The variables E equals 12V and RT equals 40 ohms. 12V substitute variables. I equals 40 ohms. Current in circuits. I equals 0.3A. Ohm's law describes the relationship between the variables of voltage, current, and resistance that is linear and easy to illustrate with a few extra calculations. First is the act of changing the total resistance of the circuit, while the other two remain constant. In this example, the RT of the circuit in figure 12-82 is doubled. The effects on the total current in the circuit are: formula, E equals I, R. E solved for current, I equals R. The variables: E equals 12V, and RT equals 80 ohms. 12V substitute variables: I equals 80 ohms. Current in circuits: I equals 0.15A. It can be seen quantitatively and intuitively that when the resistance of the circuit is doubled, the current is reduced by half the original value, R1, 10 ohms, plus 12V, dash, R2, 30 ohms. Figure 12-82. Simple DC circuit with additional resistor. 12-35. Next, reduce the RT of the circuit in figure 12-82 to half of its original value. The effects on the total current are: formula, E equals I, R. E solved for current, I equals R. The variables: E equals 12V, and RT equals 20 ohms. 12V substitute variables: I equals 20 ohms. Current in circuits: I equals 0.6A. Voltage drops and further application of Ohm's law. The example circuit in figure 12-83 is used to illustrate the idea of voltage drop. It is important to differentiate between voltage and voltage drop when discussing series circuits. Voltage drop refers to the loss in electrical pressure or EMF caused by forcing electrons through a resistor. Because there are two resistors in the example, there are separate voltage drops. Each drop is associated with each individual resistor. The amount of electrical pressure required to force a given number of electrons through a resistance is proportional to the size of the resistor. In figure 12-83, the values used to illustrate the idea of voltage drop are: current, I equals 1 mA, R1 equals 1 k ohms, R2 equals 3 k ohms, R3 equals 5 k ohms. The voltage drop across each resistor is calculated using Ohm's law. The drop for each resistor is the product of each resistance and the total current in the circuit. Keep in mind that the same current flows through series resistor. Formula, E equals I, R. Voltage across R1, E1 equals IT, R1, E1 equals 1 mA, 1 k ohms, equals 1 volt. Voltage across R2, E2 equals IT, R2, E2 equals 1 mA, 3 k ohms, equals 3 volt. Voltage across R3, E3 equals IT, R3, E3 equals 1 mA, 5 k ohms, equals 5 volt. R1 IT 1 mA, 1 k ohms, plus, dash, R2, 3 k ohms, R3, 5 k ohms. Figure 12-83. Example of 3 resistors in series. The source voltage can now be determined, which can then be used to confirm the calculations for each voltage drop. Using Ohm's law, formula, E equals I, R. Source voltage equals current times the total resistance ES equals I, RT. RT equals 1 k ohms plus 3 k ohms plus 5 k ohms, RT equals 9 k ohms. Now, ES equals I, RT. Substitute ES equals 1 mA, 9 k ohms, ES equals 9 volts. Simple checks to confirm the calculation, and to illustrate the concept of the voltage drop, add up the individual values of the voltage drops, and compare them to the results of the above calculation. 1 volt plus 3 volts plus 5 volts equals 9 volts. Voltage sources in series. A voltage source is an energy source that provides a constant voltage to a load. 2 or more of these sources in series equals the algebraic sum of all the sources connected in series. The significance of pointing out the algebraic sum is to indicate that the polarity of the sources must be considered when adding up the sources. The polarity is indicated by a plus or minus sign depending on the source's position in the circuit. In figure 12-84, all of the sources are in the same direction in terms of their polarity. All of the voltages have the same sign when added up. In the case of figure 12-84, 3 cells of a value of 1.5 volts are in series with the polarity in the same direction. The addition is simple enough. ET equals 1.5V plus 1.5V plus 1.5V equals plus 4.5 volts. 12-36. 1.5V 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 plus Figure 12-84. Voltage sources in series add algebraically. However, in figure 12-85, one of the 3 sources has been turned around, and the polarity opposes the other 2 sources. Again, the addition is simple. ET equals plus 1.5V minus 1.5V plus 1.5V equals plus 1.5 volts. Kirchhoff's voltage law. A law of basic importance to the analysis of an electrical circuit is Kirchhoff's voltage law. This law simply states that the algebraic sum of all voltages around a closed path or loop is 0. Another way of saying it, the sum of all the voltage drops equals the total source voltage.
A simplified formula showing this law is shown below, with 3 resistors in the circuit, ES minus E1 minus E2 minus E3 minus EN equals 0 volts. Notice that the sign of the source is opposite that of the individual voltage drops. Therefore, the algebraic sum equals 0. Written another way, ES equals E1 plus E2 plus E3 plus EN. The source voltage equals the sum of the voltage drops. The polarity of the voltage drop is determined by the direction of the current flow. When going around the circuit, notice that the polarity of the resistor is opposite that of the source voltage. The positive on the resistor is facing the positive on the source, and the negative on the resistor is facing the negative on the source. Figure 12-86 illustrates the very basic idea of Kirchhoff's voltage law. There are 2 resistors in this example. One has a drop of 14 volts, and the other has a drop of 10 volts. The source voltage must equal the sum of the voltage drops around the circuit. By inspection, it is easy to determine the source voltage as 24 volts. Figure 12-87 shows a series circuit with 3 voltage drops, and 1 voltage source rated at 24 volts. 2 of the voltage drops are known. However, the third is not known. Using Kirchhoff's voltage law, the third voltage drop can be determined. With 3 resistors in the circuit, ES minus E1 minus E2 minus E3 equals 0 volts. Substitute the known values. 24V minus 12V minus 10V minus E3 equals 0. Collect known values. 2V minus E3 equals 0. Solve for the unknown. E3 equals 2 volts. 14V plus ES equals 24V plus 10V. Figure 12-86. Kirchhoff's voltage law. 1.5V 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 plus E1 12V dash plus EE24V2 S dash 10V plus dash E3 plus. Figure 12-85. Voltage sources add algebraically. 1 source reversed. Figure 12-87. Determine the unknown voltage drop. 12-37. Determine the value of E4 in figure 12-88. For this example, I equals 200 mA. First, the voltage drop across each of the individual resistors must be determined. E1 equals I, R1, E1 equals 200 mA, 10 ohms. Voltage drop across R1, E1 equals 2 volts. E2 equals I, R2, E2 equals 200 mA, 50 ohms. Voltage drop across R2, E2 equals 10 volts. E3 equals I, R3, E3 equals 200 mA, 100 ohms. Voltage drop across R3, E3 equals 20 volts. Kirchhoff's voltage law is now employed to determine the voltage drop across E4. With 4 resistors in the circuit, ES minus E1 minus E2 minus E3 minus E4 equals 0 volts. Substituting values. 100V minus 2V minus 10V minus 20V minus E4 equals 0. Combine. 68V minus E4 equals 0. Solve for unknown. E4 equals 68V. Using Ohm's law and substituting in E4. The value for R4 can now be determined. Ohm's law, EI, R equals E4 specific application, R4 equals I. 68V substitute values, R4 equals 200 mA. Value for R4 equals 340 ohms. Voltage dividers. Voltage dividers are devices that make it possible to obtain more than one voltage from a single power source. A voltage divider usually consists of a resistor, or resistors connected in series, with fixed or movable contacts, and 2 fixed terminal contacts. As current flows through the resistor, different voltages can be obtained between the contacts. Series circuits are used for voltage dividers. The voltage divider rule allows the technician to calculate the voltage across one, or a combination of series resistors without having to first plus R1 10 ohms dash plus E100 Vs dash plus R2 50 ohms dash plus R4 R3 plus 100 ohms. Figure 12-88. Determine the unknown voltage drop. Calculate the current in the circuit. Figure 12-89. Because the current flows through each resistor, the voltage drops are proportional to the ohmic values of the constituent resistors. To understand how a voltage divider works, examine figure 12-90 carefully and observe the following. Each load draws a given amount of current, I1, I2, I3. In addition to the load currents, some bleeder current, IB, flows. The current, IT, is drawn from the power source and is equal to the sum of all currents. The voltage at each point is measured with respect to a common point. Note that the common point is the point at which the total current, IT, divides into separate currents, I1, I2, I3. Each part of the voltage divider has a different current flowing in it. The current distribution is as follows. Through R1, the leader current, IB, through R2, IB plus I1. Through R3, IB minus I1, plus I2. The voltage across each resistor of the voltage divider is 90 volts across R1, 60 volts across R2, 50 volts across R3. CBA. R2 R3. R1. Figure 12-89. A voltage divider circuit. 12-38. IT. 200V. R3. 150V. RE2. 90V. R1. Load. IT. IBI 1 I2 I3. Figure 12-90. A typical voltage divider. The voltage divider circuit discussed up to this point has had one side of the power supply, battery, at ground potential. In figure 12-91, the common reference point, ground symbol, has been moved to a different point on the voltage divider. The voltage drop across R1 is 20 volts. However, since tap A is connected to a point in the circuit that is at the same potential as the negative side of the battery, the voltage between tap A and the reference point is a negative 20 volts. Since resistors R2 and R3 are connected to the positive side of the battery, the voltages between the reference point and tap B or C are positive. The following rules provide a simple method of determining negative and positive voltages. 1. If current enters a resistance flowing away from the reference point, the voltage drop across that resistance is positive in respect to the reference point. 2. If current flows out of a resistance toward the reference point, the voltage drop across that resistance is negative in respect to the reference point. It is the location of the reference point that determines whether a voltage is negative or positive. Tracing the current flow provides a means for determining the voltage polarity. Figure 12-92 shows the same circuit with the polarities of the voltage drops and the direction of current flow indicated. The current flows from the negative side of the battery to R1. Tap A is at the same potential as the negative terminal of the battery since the slight voltage drop caused by the resistance of the conductor is disregarded. However, 20 volts of the source voltage are required to force the current through R1. And this 20-volt drop has the polarity indicated. Stated another way, there are only 80 volts of electrical pressure left in the circuit on the ground side of R1. When the current reaches tap B, 30 more volts have been used to move the electrons through R2, and in a similar manner the remaining 50 volts are used for R3. But the voltages across R2 and R3 are positive voltages, since they are above ground potential. Figure 12-93 shows the voltage divider used previously. The voltage drops across the resistances are the same. However, the reference point, ground, has been changed. The voltage, R3 R2 R1, CBA, plus 30V minus 20V, plus 50V plus 100V, CBA, 50V 30V 20V, R3 equals 100 omega, R2 equals 60 omega, R1 equals 40 omega. Figure 12-92. Current flow through a voltage divider. CBA, 50V 30V 20V, R3 R2 R1, 100V. Figure 12-91. Positive and negative voltage on a voltage divider. Figure 12-93. Voltage divider with changed ground. 12-39. Between ground and tap A is now a negative 100 volts, or the applied voltage. The voltage between ground and tap B is a negative 80 volts, and the voltage between ground and tap C is a negative 50 volts. Determining the voltage divider formula. Figure 12-94 shows the example network of 4 resistors and a voltage source, with a few simple calculations. A formula for determining the voltage divisions in a series circuit can be determined. The voltage drop across any particular resistor shall be called Ex, where the subscript X is the value of a particular resistor, 1, 2, 3, or 4. Using Ohm's law, the voltage drop across any resistor can be determined. Ohm's law, Ex equals I, Rx, as seen earlier in the text. The current is equal to the source voltage divided by the total resistance of the series circuit. Current, I equals ERST. The current equation can now be substituted into the equation for Ohm's law. Substitute, Ex equals ER, ST, Rx, algebraic rearrange, Ex equals RR, XT, ES. This equation is the general voltage divider formula. The explanation of this formula is that the voltage drop across 1000 omega Any resistor or combination of resistors in a series circuit is equal to the ratio of the resistance value to the total resistance, divided by the value of the source voltage. Figure 12-95 illustrates this with a network of 3 resistors and 1 voltage source. RXEX equals ESRT. RT equals 100 ohms plus 300 ohms plus 600 ohms equals 1000 ohms. ES equals 10V. Voltage drop over 100 ohms resistor is 100 ohms. EX equals 100V. E 100 ohms equals 10V. Voltage drop over 300 ohms resistor is 300 ohms. EX equals 100V 1000 ohms. E 100 ohms equals 30V. Voltage drop over 600 ohms resistor is 600 ohms. EX equals 100V 1000 ohms. E 100 ohms equals 60V. Checking work. ET equals 10V plus 30V plus 60V equals 100V. Parallel DC circuits. A circuit in which 2 or more electrical resistances or loads are connected across the same voltage source is called a parallel circuit. The primary difference between the series circuit and the parallel circuit is that more than one path is provided for the current in the parallel circuit. Each of these E1 100 ohms plus ES dash plus R1 dash plus R2 dash plus R3 dash plus R4 dash E2 plus R1 plus R2 ES 100V 300 ohms E3 dash plus R3 dash 600 ohms E4. Figure 12-95. Network of 3 resistors and 1 voltage source. Figure 12-94. 4 resistor voltage divider. 12-40. Parallel paths is called a branch. The minimum requirements for a parallel circuit are the following: a power source, conductors, a resistance or load for each current path, 2 or more paths for current flow. Figure 12-96 depicts the most basic parallel circuit. Current flowing out of the source divides at point A in the diagram, and goes through R1 and R2. As more branches are added to the circuit, more paths for the source current are provided. Voltage drops. The first point to understand is that the voltage across any branch is equal to the voltage across all of the other branches.